There we go. It's okay.
I'll begin with the word prayer. Heavenly Father, we thank you for this day again. Thank you for the students. Just ask you to with us today, help us to glorify you and understand a little bit more about letting your own together, Lord. In my prayer, Jesus. Amen. So, you take off the silly mic, there's really no point. So last week we talked about orthogonal projections and how to find, basis, which is orthonormal, right? Which is dot products which are 0 if they're not the same, and 1 if they're the same. So like pairwise perpendicular and what's the word? Length 1, right? And so just to review briefly, this is the theory that we went over, roughly speaking. If you have a subspace which is a span of a particular, set of linearly independent vectors, that means an k-dimensional subspace Rn. And then we use the Gram-Schmidt algorithm. We can orthonormalize these things, and then we can also talk about the perpendicular space to W, right? As we discussed, that's the null space of the transpose of the matrix formed by just concatenating the basis of the original ones. Now you got choices here. You could either put V1 through dk here, or you could put the U1 through UK here to straight up calculate the perpendicular W, because like either the U's or the V's are, a spanning set, so you could technically use either one. Why would I use the V's rather than the U's? Simple reason. Typically the V's I give to you, they're like integers, they're nice, right? Whereas the U's, you're creating those from Gram-Schmidt, which means they've probably got fractions, or worse, you got roots. So it's just nicer to use the one without the roots if you can get away with it, so do that. And of course, by counting here, the perpendicular space has to be n minus k dimensional, so that in total we have, n dimensions to span. The spaces W and W perp are complementary spaces. Sort of like, the whiteboard and this meter stick, right? 3 dimensions, you got the plane of the board, and perpendicular direction, that's everything, right? If this is the origin, let's say. And so here's formulas for the projection of a point in Rn onto the W space or onto the W perp space. And I refer to these as x1 and x2 for the purposes of this PDF in this little subpart of our lecture today. And I'll post this PDF in Canvas, of course, once I get a chance. Soon after class, hopefully. And the thing that's neat about the W and the perp W is that they're perpendicular. So vectors in them are perpendicular, so that's what that means. In particular, the dot product of this guy and that guy is 0, which means the length of x squared is the length of that piece squared plus the length of that piece squared. All right? So what does this mean? Well, this means, the big thing it means for us is since the distance from P to Q, how do we calculate distance from P to Q? We take like Q minus P and calculate the length of the displacement vector, right? That's like the definition of distance in terms of vector length. We take the difference of the points and calculate the length of that vector. So if you think about, well, if you think about that concept paired with this, you can see that x1 is going to be the point which is on W closest to x, because if you were to calculate the distance from x to x1, well, anyway, oh goodness gracious, sorry guys. The formula for x minus x1 is x2, all right? So like, and sorry, I got my mind not there at the moment. Anyway, this could be proved if I was, oh, come on, really? I did plug you in, didn't I? Well. Seriously. this happen in other classes in here, or is it just me? Okay, so the projection onto W gives you the closest point on W to X. How far is that point from X? It's whatever the length of this piece is. Like that's how far it is from X, right? Because we can build a point in Rn as a sum of two unique vectors. We can build any point in Rn, and here's a stupid picture. If this is W, then W perp, so you can think of W as being like the plane of the board, right? And then you can think about like coming out at W perp. I take a point in 3 dimensions, there's two pieces. There's the piece which is parallel to the plane which we're talking about, and then there's a piece which is perpendicular to the plane. And X can be built as a sum of this plus that. How far is the point from the plane? It's the distance, it's the length of x2 is how far it is. The length of x2 is exactly the length of the vector x projected onto W perp. That's another way to look at it. All right. Here's a less adventurous picture. And this one kind of works for as many dimensions as you like. W goes this way, W perp goes that way. Here's your point. You can break it into two pieces, x1 and x2. Oh man, this one was like blue. It's supposed to be green. It's supposed to be blue. The camera's stupid. Anyway, so the point is there's a unique decomposition of x into a vector parallel to W and a vector parallel to W perp. And those two vectors, x1 and x2, are perpendicular. As such, the distance, how do you define the distance from a point to a line, or to a plane, or to a space? What's the distance defined to be between a point and an extended object? Like, what would the distance from me to Sam be? It's like the closest thing on him I can touch up there. So now, as defined by his hair, that my distance, now you're 1 meter, apparently. Oh, I misspoke. You're 1 yard from me. There we go. Here it is, a yardstick. What's this? How dare we have such an arcane measurement device? We should have a meter stick. Man, sad. Okay, anyway, so the distance from X to, the distance from X to W is simply the distance from X to X1. And because X is equal to X1 plus X2, X minus X1 is X2, and so that's the distance. The length of the piece of the point, which is not in the space, it gives you the distance in the space, actually. So here's an example with actual numbers in it. Because I think a good part of your homework is basically this. Yep. I mean, if you look at the problems from the book, they're essentially using these ideas from what I saw. Or they're just like make an orthonormal set, or calculate coordinates with it. Now, the first couple problems are with respect to an orthogonal basis. What's the difference? I've been telling you guys, you find that like the components with respect to an orthogonal basis just by taking dot products, right? But if we have an orthogonal basis, we can't just take dot products, we have to also divide by the lengths, right? Because, well, anyway, you'll figure it out, but just a warning. Orthogonal is not the same as orthonormal. Orthonormal is super nice. Orthogonal, just nice. So, so here's W. I just made it up. And I gave us, for the sake of, well, actually I didn't make it perpendicular, right? This dot that is not 0. But I can tell you what this is. Those are two vectors which are tangent to the plane x plus y plus z equals to like 0. All right, they're in the plane, the normal, 1, 1, 1. You can usually verify that 1, 1, 1, dot product with this or that is 0, which is saying that this plane, formed by the span of these two vectors, must be the plane with normal 1, 1, 1. Okay, great. Then what? Well, I decided it would be most interesting and lazy to calculate the projection onto W perp here, because the problem of finding an orthonormal basis for W perp is the problem of dividing by. I shouldn't make jokes, even the ones I made for myself. 1 over the square root of 3, 1, 1, 1 is the orthonormal basis. I just had to normalize it. All right, great. So then I take the dot product of this with the vector times the vector. I pull out 1 over 3, 1 over 3, giving 1/3, and I apparently 444 is the projection of 345 onto the perp to W. Okay, so then by the complementary, the projection onto W is simply this minus that. Now, why didn't I just calculate projection of W directly here? Why did I do it this way? This is kind of like a circuitous, like I'm not using the formula I had in the sheet, page 1, right? Why? I mean, I could have, right? But that would have been a drag because I would have had to like Gram-Schmidt these vectors, right? Which wouldn't have been a big deal, but it would have been like more trouble than what I did. So it's just easier in this context to take the vector minus the projection onto the perpendicular space to find the projection onto the space in this context. And when I did that, I get minus 1, 0, 1. So what that means, to summarize, what does this all mean? It means that minus 1, 0, 1 is the point on W, which is closest to the point 345, and the distance from 345 is given by the length of the perpendicular piece dated 444. So it's this point 345 is distance square root of 48 from the closest point, which happens to be minus 1, 0, 1. Does that make sense? Yes, no, think so? Well, think about it. You got a couple homework problems to try to help that settle in. Example 2. I made myself, I was nice. I was kind to myself. I gave myself orthogonal spanning sets. See, like the dot product of this and that with each other, 0. The dot product of this and that with each other, 0. And also with this and that, and this and that, and this and that, and this and that, and this and that. Yeah. It's an orthogonal, those 5 vectors are orthogonal. Right? So that's great. Which means that I can skip the laborious step of Gram-Schmitting them to find orthonormal bases, right? We did that last week. It's time intensive for lecture. So let's go on. Now here, all I had to do, why am I dividing by root 2? Why didn't I divide by root 2 over here? You guys can help me? Because magnitude, right? I'm dividing by magnitude, I'm normalizing. That's why I divide by root 2 over here. So for kicks, rather than doing a specific numerical point, I thought I'd bring letters into the mix as to confuse the students. And so here they are. The projection onto the point ABCDE in the W direction is given by the dot product of the point with the orthonormal basis, using those as weights. And I get this point right here. That's my x1. And the projection onto the perp, I only have 2 things to deal with there. Notice that the half is because I got a root 2 and a root 2 in both of those, so root 2 squared is just a half. That's just a convenient way to calculate. And there's your projection into the perp of W. And what happens when you add these 2 formulas? See it? This plus this gives me A. This plus this gives me B. This plus this, C. This plus that, D. This plus that, E. In other words, x1 plus x2 is D, as it ought to be. And once you have these, you can easily calculate the distance from any point, for any point in 5 dimensions. The distance, you can find the point in 5 dimensions, which is closest to either the space W or the space W perp, right? Either one you can do. If you wanted to find the point closest to W perp, you use this formula, right? And how far is it from W perp? It's the length of the red part. If you wanted to find the point closest to W, you use this point. How far is it from W? The length of that, whatever that is. So there's a complete symmetry between the roles of W and W perp. I wrote down some formulas for orth last week. Those are useful. But anyway, there it is. So I just wanted to go back over this again with a couple of actual examples because I talked a lot about the theory last week, but I didn't give you any actual examples, so I thought this might be helpful to you as you're thinking about homework. Any questions? Yeah.
So do you have to use Gram-Schmidt on the subspace before you can do this stuff?
Well, yes and no. I mean, the problem is, if you don't use Gram-Schmidt, how are you getting the linear combination of the basis vectors, which forms the vector in that subspace. See, with Gram-Schmidt, I can just take dot products. The formulas for projection, you know, like x dot u times u, well, x dot uj times uj, sum j equals 1 to k. That would have to be replaced with a calculation figuring out what exactly the component of the vector is in the w direction. So you could do that, but you have to come up with the analog of that for your basis, which would be other. So I think it's easier just to do Gram-Schmidt. I mean, could you build the orthogonal projection formulas without normalizing? Could you build like orthogonal analogs to those fairly easily? Sure, that you can do. Like normalization is kind of just a convenience, but the orthogonality I think is important. It's I would say your question is somewhat akin to the question of, do I have to use a symmetric matrix for a quadratic form? I mean, you don't have to. But if you don't use a quadratic matrix for if you don't use a symmetric matrix for a quadratic form, then you lose theorems which make it super nice to analyze in terms of eigenvectors. So, yeah. Here, let's talk about the least squares problem here. So here's the deal. We're trying to solve, we'd like to solve AX equals to B when, for B, you know, and this is not written in stone, but possibly not an element of the column space of A. All right? So, so what Lay likes to do is he likes to say, basically he thinks about it in terms of something like this. So we're basically trying to take AX minus B, let's call it, I don't think he does this, but I'm gonna do it, E for like the error vector. All right, you'd like to make that as small as possible. All right, make that as small as possible. And so the way to think about that is the B vector, we can break into two pieces. We can talk about B hat plus, well, I guess I don't have to come up with a name for it, but let me, I'll say B superb there, that is. So here, B hat is an element, well, let me just say B hat is equal to the projection onto the column space of A of B. All right, so like B hat is a linear combination of the columns of B. All right. All right. So then, if you look at it, we can do like this. We can say, okay, so what I've got is I've got AX minus, and so I'm basically going from here and rewriting it as B hat plus B minus B hat. All right. That's a lot. Now, why would I do that? Let me write it again and emphasize what's going on here. So here we have AX minus B hat, right? And then plus, well, how do I want to write that? Oh, yeah. Plus, oh, my notes have an error. Doesn't matter. I guess I'll just say minus here. This piece right here, though, what is it? This is an element of what? That's an element of the column space of A, see? Why is that? Do you guys understand why that's in the column space? AX is literally a linear combination of columns of A, right? And B hat is a projection onto the column space. So by construction of the projection, this is an element of the column space. And when we take two things in the column space, we add them or subtract them, we're still in the column space, okay? That's a property of column space. So this right here is in the column space. On the other hand, how about this? Like B, what's B minus B hat? Where's that?
Perpendicular to the column space.
It is indeed perpendicular to the column space. I suppose if I remind you guys, like worth in the column space of A of B is equal to B minus the projection, which in our current notation is B minus B hat. So I suppose, technically speaking, not including the minus, this is worth column space of A of B, right? Which means, like you said, it's in the perpendicular to the column space. So we've got two vectors, one in the column space, one in the orthogonal complement to the column space, right? So like this is an element of the column space of A per. So, great, then what? What happens if we take this equation and say, multiply by A transpose, what happens? Well, let me say it this way. Let me not do that just yet. Instead, let's look at it this way. So the length of AX minus B hat, right, squared, plus the length of B minus B hat squared is equal to epsilon squared, right? So there's only one variable here, right? B is given, A is given, right? For the problem, the matrix A is given, that defines the system we're looking at. B is given, it's part of the system, right? So everything here is given except for this. This is the only variable, right? So how can we minimize the error? What do you want to do to this piece right here? You want to make it what? Small. What's the smallest it could be? 0, right? So if we make that 0, that's the smallest error. So if we have AX equal to B hat, this gives an error equal to the length of B minus B hat. Excuse me. All right, so, goodness gracious. Moving on here. Whew. So how do we, I guess the next question then is, how do you solve how to solve AX equal to B hat, right? Remember, B hat is the projection onto the column space of A of B, right? So, what does that mean for us if we accept our usual mode of operation in the last week of lectures? We need to Gram-Schmidt the column space of A, right? And do all that, that seems like a lot of trouble, right? But thankfully, you don't have to usually do that. Because you can make this kind of sneaky move here. What happens if we do, let's see here, like AX minus B is equal to the projection on the column space of A of B minus B, right? So this is what, minus the north of the column space of A acting on B, right? So then, what happens, given that, if we multiply by the transpose on both sides, what do we get? See, this is an element of the null space of A transpose, right? That is another way of writing the perp to the column space. It's the null space of A transpose, right? So what that means is if you multiply that by A transpose, that vector orth, that orth vector there, multiplying by A transpose, you just get 0. So you find that what we have to solve is A transpose AX is equal to A transpose B. These right here are the equations that give you the so-called least squares solution to the problem. So you solve those to find the least squares solution. Now, so solving this for X gives best approximation to AX equals to B, right? So sometimes people introduce a different letter just to emphasize it's not actually a solution for AX equals to B, right? If B is not in the column space of A, there is no solution possible, right? But this will give us the best approximation. Excuse me. And I explained to you guys, like last class, how the QR decomposition would help even more with that. Can I, I'll give you guys a second. Are you guys done writing that down? I gotta put the projector back down. We're planning on my part. Phones at the ready. I like it when it makes the clicking noise. That makes it very satisfying. I feel like you really did something. Let's see here. Oh, yeah. I do have some pretty good examples of these squares in the notes, so let's look at those. So here's the so-called linear least squares problem. By the way, these equations I just wrote down. Oh, here's the SNASB proof in my notes for what we just did. Like, this is equivalent to the calculation we just went through, but you know, if this makes more sense to you than what we wrote on the board, great. If not, whatever. The normal equations are what we derive, though. A transpose AU is equal to A transpose U. Solving those gives us the best approximation to the problem. So here's the linear least squares problem. Find values of C1 and C2, right, that closely models a given data set. So suppose you've got k points, x1, y1, x2, y2, all the way out to xk, yk. What line is closest to those k points, right? Of course, if we have more than 2 points, there's no guarantee that there's a unique line that they fit, right? So what happens here? So you plug the data into the model. And so if I plug y1, x1 in, I get y1 is c1, x1 plus c2, and y2 is c1, x2 plus c2, and they're kind of boring equations. When you write them as a matrix, you've got all these y's equals to, like this, c1, c2. Notice that the y's and the x's are given here. The c1 and c2 is what we don't know. So I can rewrite this as y is equal to mv. This is, of course, an overdetermined system. Like, it would be very surprising for this to have actually a solution, right? So what we do instead is we take it and we multiply by M transpose both sides. So M transpose M is just a 2 by 2 matrix, which we like, right? So M transpose M is a 2 by 2 matrix. M transpose Y is a column vector, two-component column vector. So this makes a very nice, like, final exam question, for example, because while it is about something interesting and new, the computation is just 2 by 2 matrix stuff, which we should all know, right? So like, to solve the normal equations, we've got a 2 by 2 matrix times a, column vector we don't know is a column vector we calculated. So multiply by the inverse of M transpose M, and voila, there you go. This is the best fit line for the data. What if instead of having, points in 2 dimensions, you've got like 3-dimensional points? So you've got triples, X, Y, Z, and you've got K of them, and you're looking for the best fit plane to these 3 points. How would you do that? Well, I just plug the points into the model, and that gives me this matrix of data times the unknown coefficient vectors C1, C2, C3, and then I solve the normal equations again. M transpose M gives me this, and so we're finding the plane which is closest to these 4 points, right? How many points fix a plane? Just 3, as long as they're not like collinear. That'd be trouble too. But yeah, so this one a little bit uglier, and I end up with the problem. This is my M transpose M, this is my M transpose Z, so we do the usual, well, I didn't write it down, I guess. It's this concatenated with that, rho reduces to this monstrosity, which gives us C1, C2, and C3. In other words, Z equals to that is the plane which is closest to the given points. It's almost embarrassing how easy this is, given some of the things we've done up to this point, right? Like, in contrast to like finding eigenvalues and eigenvector for a matrix, this is so stupidly easy, isn't it? Like, you just work out the coefficient matrix for your model, multiply by the transpose, solve. I mean, it was shocking to me when I realized how simple it is to find the best approximation to an inconsistent linear system. There are generalizations to this, of course, like nonlinear least squares. If I've got a bunch of model functions like f1 through fn, and I've got a data, but the thing is, the functions can be nonlinear, all right, but the coefficients are appearing linearly. If that's the case, when you plug the data set in, you're still going to get like a linear equation in unknown coefficients, which means that you're still getting an inconsistent system with a given coefficient matrix and a given unknown homogeneous term, which again, you can solve by finding the normal equations. Now, I will admit, there is some analysis here that's missing. How do I know that that's really the best fit solution? That's just, wishful thinking on my part, really. If you were to take maybe a multivariate, maybe a, what's the word, operations research course or something, perhaps you might find other arguments to assure yourself that really are finding the best approximation. Maybe it's not the best approximation either, all right? But it's an approximation. It's making something small. Sometimes there's multiple competing approximations for something, and you can decide which one's better for your given purpose. The least squares is minimizing the distance between the data and like the square of the output. That's what it's doing. So here's one. If I have this data, I want to find the best fit parabola. So that gives me this, and again, I solve the normal equations, and what do I get? I get this, and here's a picture of it. So these 5 points are closest to that parabola. Least squares found that for me. I think it's kind of neat. You can disagree if you want. Oh, in application to physics, I won't burden you with that, but you know, if you wanted to figure out gravity on a mysterious planet, you could, you know, figure out coefficients to the, you know, constant, the projectile motion, assuming it's a vacuum, of course. Let's see, here's another one. All right, I think I've got too many examples. Let me go on here. Here's a funkier one. I don't think this matters a bit to us in this class, but it's something to be aware of. Sometimes you have a model which has coefficients which do not appear linearly. Like Newton's law of cooling with room temperature 70 has a solution that's like T of T is C naught e to the minus KT plus 70. So in that form, it wouldn't be a very good fit for least squares data fitting. But if we take the natural log of the difference between the temperature and room temperature, then we've got the log of C naught minus KT. All of a sudden, the log of C naught and K appear linearly, and we can do these squares on that meaningfully and still profit from the least squares technique. So if you have a nonlinear problem, sometimes you might be able to linearize it with like a log. Just an idea. All right, so I think that's all I got in here for the least squares stuff. So just to recap, you need to make sure you know how to Gram-Schmidt. And the other thing, of course, is to find the perpendicular space. We've used this trick a lot, right? The null space of a given space, the null space of the transpose for a generating set will give us the perpendicular to the space. We've used that trick a fair amount. That's a nice calculation because we know how to calculate null space of the matrix nicely. All right, so let's move on here then, unless there's a question. No? So the next topic we have to talk about is the question of when diagonalization doesn't happen. Like, so what if it's not diagonalizable, right? What if A in R n by n is not diagonalizable? All right, that's the question that is going to occupy our attention for a good part of this week here. So you guys tell me, when would A be diagonalizable? What's the condition for it? Let me remind you. So what we do is you could say we look at P of T. You can do it different ways. I'll just, for the sake of this discussion, say it's, you know, Pi minus A, right? This is the characteristic polynomial. A lot of times I set up the characteristic equation with the A minus lambda I instead, but just for the sake of theoretical purity, let me do it this way. That makes the formula for this something like T to the n power, right? And then plus stuff, right? Plus what? Plus minus 1 to the n times the determinant of A. That's the last thing. Now you might be wondering why minus 1 to the n times the determinant of A. You can kind of see it. If you just think about like intuitively putting t equals to 0, that should give you, P of 0 should give you the constant term, right? Like if you have a polynomial, what happens when you plug in 0? You get the constant term. So on the other hand, if I calculate the determinant of minus a, what is that? It's minus 1. How big is a? It's n by n, right? So that's why that minus 1 to the n is there. Now, of course, we can factor that. It's t minus lambda 1 times t minus lambda 2, t minus lambda n, right? Now here, we have lambda sub I possibly repeated, right? Possibly repeated, possibly complex, right? Possibly repeated, possibly complex. So, but if we're taking this complex perspective, when can I do this? When is it possible to factor an nth order polynomial? The answer is yes, it is possible. This is the fundamental theorem of algebra, right? That an nth order polynomial will factor into, it has n zeros, possibly repeated, possibly complex. This is what it looks like. Now, if I write this instead like this, so t minus lambda 1 to the m1 power, t minus lambda 2 to the m2 power, t minus lambda, let's say s, to the ms power. And here, I'm saying lambda 1, lambda 2, lambda s, distinct, right? And for the sake of specificity at the moment, let us suppose that these are distinct real eigenvalues. Now that doesn't always happen. It doesn't always happen. So I'm looking at a special case here for the sake of discussion, all right? Can you guys tell me a condition that would force that to happen? What would make your eigenvalues be all real, possibly repeated? What's a simple condition you can give on the matrix to force that to happen? This you should know already. What is a condition on a matrix which forces, in fact, diagonalizability? So we talked about the real spectral theorem, right? If a matrix is symmetric, it has an orthonormal eigenbasis. That would imply that this was the case. Now, so here's the deal. In this context, suppose that all the eigenvalues are real, right? If all the eigenvalues are real, then m sub I is the algebraic multiplicity of lambda I, okay? Algebraic multiplicity of lambda I. That's the number of times that the factor is repeated in the characteristic polynomial. Okay? If, on the other hand, you can talk about, Wi, or Wi in the sense that it's the null space of a minus lambda ii. There, I'll change that to a j. Go back down. This has dimension of wj equal to the geometric multiplicity of lambda j. So the algebraic multiplicity is the number of times that the eigenvalue is repeated in the characteristic polynomial. The geometric multiplicity is actually how many linearly independent eigenvectors you have at your disposal. One way I can characterize diagonalizability, like this is a theorem, if eigenvalues all real, and I'm calling that m sub I. What would you guys want me to call the geometric multiplicity? I may have had another letter. Want to call it n sub I? I'll call this n sub I for the sake of giving you a name. And m sub I is equal to n sub I for all I, then A is diagonalizable. Why is that? I'll tell you why. The reason for that is to say that m sub I is equal to n sub I is to say that I have enough eigenvectors for each eigenspace to fill out the whole space. And the number of those vectors is the same as the number of factors in the characteristic polynomial. Put this all together, what it means is I can take the basis for each eigenspace, put them together, and I have an eigenbasis for the whole of Rn, and that means that I can diagonalize it, like we proved before. That the matrix is diagonalizable if and only if there's an eigenbasis for the matrix. So what we're going to be talking about next class is, what if it's not? All right, and the answer to that is there's a twofold answer. The one answer is the Jordan form, which you guys have seen a little bit if you're Project C people. You're welcome. And then the other thing is the complex eigenvectors. And then there's also, of course, complex generalized eigenvectors as well. We'll talk about all that this week. So, as well as, of course, the matrix exponential, which is, I don't know, I'm going to turn off my camera I'm not using. That's a good job, good idea.